So is it on?
Yes.
Yes, sir.
Thank you. Here, let me give you another one
Thank you.
of these. Good catch. Hey.
One hand while holding another piece of paper.
What's today?
And it was his left hand.
Today is what, the 27th?
Yeah.
By the way, the White House has recommended huge cuts in basic and applied science, along with huge increases in defense spending and building and spending on a wall.
It's the right time to go to quantum computing. They just passed that huge bill.
That may be,
It's a national security issue now. China's beating us.
Okay, so let's see what it was that we were talking about. First of all, we have a Killing's condition. Flat space condition. So this is when x prime I is xi plus epsilon yi. This Killing vector should satisfy the kth derivative of the ith component plus the ith derivative of the kth component should be 2 over the number of dimensions, the flat space metric, and then the divergence of y, which is, say, yl comma l. So that's something that we came to some time ago, and so the general transformation for flat space that we call a conformal transformation is x prime I is xi plus a translation ai plus a Lorentz transformation bik xk plus a dilation c xi plus a what's called a conformal transformation in the narrow sense, a to ik x squared minus 2xi xk, and here of course x squared is xl xl. We're in flat space. It's probably worthwhile writing down these commutation relations just because they're so important. So these are the translation operators. These generate translations. They're the energy momentum 4 vector. And then there's a conformal 4 vector k. Why it's spelled with a K and not a C, I don't know. Again, this may have been done in German first and then in English. Then we have the dilation generator with a momentum, and that's minus pi. The dilation operator with the generators of Lorentz transformations is 0. That's saying that the dilation operator is a scalar under Lorentz transformations. dki is ki, and these two things are similar, namely that 4 vectors dilate and this one dilates with a positive +1, and this dilates with a -1. And the reason is, well, one can trace the reason back to the fact that the momentum operator is a derivative with respect to x, and this is kind of multiplication by x. Then there are some less trivial one, well, I shouldn't say less trivial. This Jij PL, and this is minus eta IL PJ plus eta JL PI. This is saying that the momentum generators of space-time translations are a 4-vector under Lorentz transformations. Similarly, JIJKL is minus eta IL KJ plus eta JL KI, and that's saying that the generator of conformal transformations is a 4-vector, also under Lorentz transformations. Then there's the commutator of 2 generators of Lorentz transformations, and this is minus eta IL JJM minus eta JM JIL plus eta JL JIM plus eta IM JL. Wait a minute, I screwed up. There's something wrong here. IMJL, okay. JLI, all right, this apparently is right. Okay. And the last one is that the generator of a Lorentz, of a conformal transformation commuted with the generator of a space-time translation is 2Jij plus 2 eta ij d dilation. One interesting thing is that if you add up all of these generators in d dimensions, there are d p's, there are dk's. For j's, there are d minus 1 over 2 j's. This again is d space-time dimensions, and there's 1d. If you add them together, it's a total of d plus 2, d plus 1 over 2 generators of the conformal group in d dimensions. And that's the same number as the group SOD, SOD plus 2, and also SOD comma 2. And so in other words, if you're in a space-time where everything is Euclidean, then it's just SOD plus 2. But if you're in a quasi-Minkowski space-time with that is to say, if you're in an ordinary Minkowski space-time, and so your Lorentz group is SO D1, then for this space-time, the conformal group is SO D(2). And so, in other words, the conformal group for actually, I made a mistake. This is D-1. So if you're in D-dimensional Minkowski space, D-1 space dimensions, 1 time dimension, the corresponding conformal group is D2. And that conformal group is the same as the Lorentz group for a space-time with D space dimensions and 2 time dimensions. Now, what the significance of that is, I don't know. But it's, I invite you to think about it. It's probably more interesting than most things on Netflix. Well, there are some good things on Netflix. And in fact, I think Netflix is actually altogether I think it's altogether a good thing because there are, I think it spreads ideas that make sense, such as atheism. Yeah.
So I guess like finding is is kind of what you're saying. Finding representations of the conformal group in D-dimensional Minkowski space is the same as just finding representations of S of D(2).
Finding representations of the conformal group
in D-dimensional Minkowski space
is the same as the representations of the Lorentz group in D space and 2 times.
Yeah, but representing it on the smaller space of the D-dimensional Minkowski space.
Yeah.
Basically.
Okay, so
before we go, can I just, we're gaining that extra spatial dimension in the conformal group.
I'm sorry, say it again.
The reason I think that we gain that extra spatial dimension in the conformal group.
We gain 2 extra dimensions, 1 extra time and 1
I'm
extra
sure
space.
that the extra spatial dimension is because there's 1 extra spatial, I guess, well, yeah, for time too. There's 2 additional, the number of generators are the same, but there's 2 additional operations, right?
There are 2 new generators, that's for sure.
Yeah, I don't know where the additional, the time transformation.
All right, look.
It's
I don't know what this means. It's let me just mention one thing to you that is a little closer to ordinary physics, and it is that let me see if I have this right. In ordinary 3 plus 1, for D equal to 3 plus 1 dimensions, which is apparently where we are, this basic spinner is a Dirac 4-spinner, psi D, or it could be Majorana. Anyway, it's a 4-spinner, which is, let us say, a 2-dimensional left-handed spinner on top of a 2-dimensional right-handed spinner. Now, if on the other hand we are in 4 plus 1 dimensions, then the basic spinners are 4-dimensional. This is the basic spinner. So in other words, the reason why we have everything as, in other words, where the fermions, let's leave aside the neutrinos because they're still unsettled, we don't know quite what's going on. But for the quarks and the charged leptons, they're represented basically, at least for the electromagnetic and strong interactions, as 4-dimensional spinners, and 4-component spinners, and we would expect that to be the case if we had if we were living in 5 dimensions. This is described, I hadn't intended to talk about this today. This is described more carefully in Chapter 5 of Weinberg Volume 1, which we covered more or less, which we talked about, which we used in the first semester. All right, so let's now look at a particular theory, namely the Maxwell action. And what we'll see is that it is scale and conformal invariant. And I don't know how to say that in English. I would say conformally invariant, but can I say scaly invariant? All right, what the hell? It is scaly invariant and conformally invariant.
That's what it's invariant and scaling.
Wait, why doesn't conformally invariant imply scale invariant?
All right,
Because we have dilations, right?
that's a matter. That's a matter of usage. I think we should go with Austin's usage.
Yeah, because the dilation is just a generalization of a scaling.
Okay, by which we mean invariant under the Poincare group, the dilations, and the specifically conformal transformations. Okay, now, what happens to the electromagnetic field under such a transformation? Well, in general, a covariant vector field transforms this way. It's xk comma I prime ak of x, which is, if I write it out really explicitly, so that's how a covariant vector field transforms under an arbitrary coordinate transformation. Now what we're going to do is we're going to have a tiny change. X prime I, say, is xi minus yi, which is equivalent to xi equals x prime I plus yi. Now, notice, normally you have a plus sign here, but it turns out the calculation that I'm about to start, and which took me quite a long time with my fingers, and quite a long time with LaTeX to write up, it turns out that it's easier to put in a minus sign at the very beginning. Okay, if we do this, then what is the change in AI of x? And by that, I'm going to mean a prime I of x minus a I of x. So at a given point x, how does the field change? And we can rewrite this as a prime I of x minus a prime I of x prime plus a prime I of x prime minus a I of x. And we're going to write it that way. And now, how does this go? Well, we can imagine that this is just the same field, and we're just changing the coordinates. And so this is yj a prime I comma j at x prime. So this is just the first power, the first term in a Taylor series expansion of this quantity in terms of that quantity. Well, of this, yeah, of this one, about that. And then the second difference, so AI prime of x prime, that's basically this, and that difference is simply, I think I put something extra here in the, so that's the change in, that's basically this thing here. Right, okay.
Is that an Irish?
Maybe I should do this in 2 steps. Let me do it in 2 steps. This is the way it is in my notes. So, delta ji plus yj comma I prime a j of x minus a I of x. Okay. So this is the full-blown thing here, expanded. In other words, what this really is this thing is this. And so this term, now I've gotten myself confused. Right, oh, yeah, you see the derivative of x, with, in other words, xk is x prime k plus yk. So that's where the delta and then the derivative. Okay. So now what we can say is that the change in AI of x is yj a prime I comma j of x prime plus yj comma I prime a j of x. Okay, now we take advantage of the fact that this is an infinitesimal transformation. So, in other words, y is tiny. And since y is tiny, we can ignore things that are second order in y. And one of these things that is second order in y is the difference between a prime of x prime and a of x. And so what we're going to say now is, we're simply going to say the change in AI of x is yj ai comma j, well, of x, plus yj comma I aj of x. Keeping in mind that all these changes, a to a prime and x to x prime, are linear in y, which is infinitesimal, and we already have a right-hand side that has 1 power of y. We don't want to keep 2 powers of y. Okay, so now what we do is we look at the change in the Faraday tensor fik, and so this is the change in diak minus dkai, and just let me mention that of course it's arbitrary whether you call fik diak minus dkai or minus that. And in the literature, you see, of course, you see both. One other thing to keep in mind is that if you use the common notation, then this becomes AK comma I, whereas this is AIK, and we have then AK comma I, whereas here it's DIAK. So there are all those things to keep track of.
So Kevin, I just have one quick question. So whenever you
Yeah.
say the Maxwell
All right,
action,
wait a minute, you guys, some of you have asked questions and I haven't given Candy. You asked something, right? Or at least you said something. Bobby, did you say something? Anybody else say something? All right, there you go.
Oh, thanks. Yeah, so, no, I was just going to ask real quick, the Maxwell action, whenever you say, this is nothing new. This is just the minus 1/4 F mu nu F mu nu.
Yeah.
Yeah, okay.
This is free electrodynamics. All right, so the change in this thing, the change in the derivative is the derivative of the change, and so let me just write this as and now we're going to plug in, let's see, which formula? I guess we're going to plug in this formula, but I'm suppressing explicit mention of x. And so this is di yj ak comma j plus yj comma k aj minus dk yj ai comma j plus yj comma I aj. By the way, these last couple of lectures I've been following a book by Anthony Z, which is, I think it's called Einstein Gravity in a Nutshell. This is somewhere in chapter 9 or 10 or something. Anyways, around page 600. All right, now if we expand this, what we get is yj, dj. It turns out we can combine a couple of these because we can combine we pull out the dj. This comma j I pulled out as dj. And then I took diak, that's the first part of fik, and then I went down here and I pulled out the yj and let the dk act on ai, and then pulled out the comma j as a dj. So altogether we've got that term, and then we have several more terms. Plus yj comma I ak comma j minus yj comma k ai comma j plus yj comma ki. This term is going to cancel, by the way, because it's followed by minus yj comma ik aj. So obviously these two terms cancel. And then we have plus y j comma k dij minus y j comma I dk aj. All right, so let's just notice that we can forget what's in the circle. And if we combine what's left together, what we get is yj dj fik plus yj comma I fjk plus yj comma k fij. By the way, I think quite highly of all of Z's books. They have the great advantage that they're readable. The part that's kind of funny about the books, though, is the in a nutshell part.
Is there like
The
this?
book, the book on gravity is about 1,000 pages, and
QFT blue.
but it's
Yeah, they're good. They're good. Yeah, I like it.
but on the other hand, Princeton University Press published the thing in a form you can actually put on a desk and it opens flat and you can read it, whereas it was also Princeton that published Monday, Tuesday, Wednesday. And that book is almost impossible to read because of its size and the way it was published. The inner margins are tiny, the outer margins are uselessly large, and all the text is on a curved surface.
Which is.
And the book is about yay big and weighs about 50 pounds.
I think
so,
that
unless you're a
is-
sumo wrestler, you can't really read the book conveniently.
I
Okay,
think that's the largest currently used scientific textbook.
It's certainly the largest.
I think it's like there's somebody like recorded these and that was with the part of the scale that of all the books used in physics that was the largest.
Yeah, well, it's a wonderful book, but it's a terrible publication, and I think the people guilty of this are the people who are in the marketing department of various publishing houses have really made many fine books inaccessible, or not totally inaccessible, but far less useful than they would be otherwise. So now that we figured out how the Faraday tensor changes, we can figure out how Maxwell's action density changes. And of course, this is 2 Fik, the change in Fik. And so that means it's 2 Fik, what I just wrote down, which is yj dj Fik plus yji fjk plus yjk fij. Okay, now we can combine some of these things, namely, we've got here Fik, 2 Fik derivative, the jth derivative of Fik. That is dj on the action density. And then Then we're going to add and subtract a term. In other words, we're going to write this as the change in Fik. We're going to say this is dj of yj Fik. And then we're going to say minus del dot y. Del dot y, of course, is just y L comma L. And then we're going to add in, and then the rest of this is 2yj comma I Fik plus 2yj comma k Fik Fij. And so I'm going to keep these two terms. And now I'm going to lower this j and raise that j, and I'm going to lower this j and raise that j. And so this is plus 2 yj comma I Fik Fjk plus 2 yj comma k Fik Fij. By the way, the LaTeX, you may wonder, how do you write this subscript so that it doesn't occur here in LaTeX? What you do is this thing here is underscore parenthesis phantom j k.
So what phantom, it's worth
This is an
noting,
underscore, right?
it's worth noting what phantom does, that function in LaTeX, is it puts a two-point math mode margin in there, so it will, in other words, all it is just a blank spot.
Yeah, it's a blank spot the
Yeah.
size of j.
Yeah,
Exactly. Change the letter, it changes the
exactly. So
space.
it just, whatever size, it's just twice, it puts it twice the distance it would have.
By the way, since I brought up LaTeX, Tech Shop has a rather nice feature that I only learned about a few weeks ago. Namely that instead of typing commands like begin equation or begin a line, you just type \BEG. No, you just type BEQ and then hit escape, and it fills in begin equation, end equation. And if you type \FRA and hit escape, it fills out a fraction. You do \BSP, it'll do a split for you. If you want to do, anyway, I don't know the full range of things that it does, but it does completions for a large number of things and saves an enormous amount of time.
You can also set it, you can customize like short, quick keys like that in it, I think, too, where it will...
Yeah, but it's a lot nicer to use the escape key, and rather than my files are littered with all sorts of macros that I wrote down that do these, that play the same role as the escape key, but the escape key is better. Okay.
Is that just for readability, that space that we're using there, or is there an actual
Well, the
notational
trouble
meaning
is
to
if the K fell here, you wouldn't know if this was the first index or the second index.
I see, okay.
I think also like last
So you
semester.
see, in other words,
we
a
used the term
tensor,
non-common.
which is the first index, which is the second, that makes a difference. and whether it's up or down makes a difference, and so you want to keep both of them. All right, so let me stop with the latex stuff. Okay, so where am I?
The best thing is to use conference.
All right, I'm going to do this one more time. And the next change is plus 2y. Oh, I already did that. Okay, so I don't need to do that. So, yeah. So now you can combine these two. And the way you combine these two is you interchange, I guess, I and k. Let me see if I've got this straight. All right, let's say you interchange I and k here. Then this would be yj comma I f ki f kj, and now what you can do is you can say, well, that's the same thing as yj comma I. You have a minus sign if you turn it to ik here. And then if you interchange these two, you get another minus sign. But this is the same thing as that. So this thing is altogether plus 4yj comma I fik fkj. Whoops, no, sorry, fjk. And so let me now write this in full. It's partial j, yj, and y being the infinitesimal killing vector, fik. And normally the killing vector isn't infinitesimal, but here I've absorbed an infinitesimal epsilon into the finite killing vector to make something infinitesimal, just so we don't have epsilons all over. So then this is minus del dot y fik plus 4, and now I'm interchanging k and j. So this becomes y k comma I fij fkj. Okay, so that's the form we want, and we can rewrite this yet again as dj yj fik plus 2 fij fkj. And now what we do here is we split this up into two terms, and we call this yk comma I plus yi comma k. And then this one we rewrite as minus a half eta ik, let us say yl comma l, or del dot y, I don't know which is more reasonable. Okay, so that's the expression. But now when you see this form here, you can see that if y isn't an arbitrary vector, but in fact is a killing vector, then we can use the second equation that I wrote down today, namely that this in fact is equal to dj of yj fik plus 2 fij fkj times 2 over d eta ik yl comma l minus a half eta ik yl comma l. Or, okay, well, I could write that in a better form, but there's no real need to. Notice, if we're in 4 dimensions, if d is 4, 2 over 4 is a half, that cancels this a half, this term goes away. So this is equivalent, if and only if d is equal to 4, it's equivalent to dj yj fik. So in other words, the change in the Maxwell action under a coordinate transformation characterized by a vector y, if y is a conformal killing vector, then this has a special form, and in 4 space-time dimensions, it is a total divergence. And that's what we mean by saying, so we effectively say that the action is invariant, that is to say that the variation in the action, which is the variation, and I'm writing plus, well, all right, the variation in the integral of fik over 4 d4 x is then an integral of quarter dj yj fik d4 x, and so this is then some sort of a surface term yj fik d sigma j lower j. And I forget whether it's plus or minus sign here. The rule is that you want to have the square of the time derivatives come in with a plus sign. That's how you tell which sign to use. Okay, so this is really quite cute, and I haven't studied conformal field theories enough to tell you what the general rule is, but I think basically it's that if the action has no dimensionful parameter, then it has a good chance of being conformally invariant. And I cannot have time to write this up in detail, but maybe we could have a go at doing it on the fly. So let's look, for example, at a free scalar field.
I have just one quick question before we depart from this example.
Yeah, what's the question?
Yeah, so like the only thing different to have a general gauge field would be to have that like commutator of the A's at the end, right?
Right.
And is that thing conformally invariant?
Right, that's a great question. Why don't we, all of us together, answer it now?
Okay, why not?
That was one of the things I wanted to do, but I just didn't have time to do it. I mean, you know, this derivation actually took more time than it should have. So let's look at what the change in the field is. Let's remind ourselves what it is. Where am I here? So to lowest order, what we have is this. The change in AI is yj, ai comma j, plus yj comma I, aj. So that's what we worked out before we started to compute the change in the Faraday tensor. So now, let's see. You see, the actual action now, it's still Fik, but it's actually, it has an extra index A on it. And so this is, well, we can always say this. This is 2 Fika, the change in Faik. And the change in Faik is the change in di aka minus dk ia, and then plus f, let us say ABC, AB, AC, IK. Now, I think this comes in with a plus sign, but I'm not absolutely certain. These are the structure constants, and for a compact group, you can raise or lower them, and it doesn't make any difference. And so I just, well, actually here, since we have those guys up, we might as well put them down to make it look a little neater. But anyway, okay, so that's, actually, it would have been better if we could tell. But this is silly. Let me not do that. All right. So we've already figured out that this part is okay. So the question is, what's the change in this? And so the change in that. So delta. I'll just write it as delta f prime. AIK is FA, well, let me just write it as ABC. FABC, the change in ABI times AKC plus the change plus ABI, the change in ACK. And so this is going to be FABC. Let me put my notes down since I'm not using them at all. The change in ABI is going to be YJ ABIJ plus YJ comma I AJ right, all that times ACK and then plus ABI, and now the change, now we change, this is a B, we change B to C and I to K, so that's YJ AC KJ plus YJ comma K AC J. Okay, so the extra change in F is that So, I don't know. Let's see. I left out something, though. This is the square brackets here. So is this going to, remember the structure constants for a compact group are totally antisymmetric and real. Gosh, I don't know. I mean, by the way, my guess is that it's going to work out. And I'm saying this for a couple of reasons. One is that in this, we haven't added, when we went from ordinary to Yang-Mills, we haven't added any dimensionful parameter. Somebody's connected to the internet here, right? Bobby?
What are you looking for?
Don't you have a surface that's connected to the internet?
I do. Yep.
So why don't you Google, is pure Yang-Mills theory conformally invariant? My guess is it's going to work out, but the trouble is, we've got to somehow combine this with that and to get a total derivative, and I don't know about. What I was going to suggest doing in class was just a free scalar field. See if that would be so much simpler to do.
So it's not scalar invariant.
What's that?
It's not scalar invariant.
So
It can be.
Yeah,
pure Yang-Mills?
Pure Yang-Mills isn't scalar invariant, and this guy says here, let me see what he just said. He says, no, Yang-Mills isn't scalar invariant. Scalar invariance is broken by the running of the coupling constant with energy. I'm not so sure what he means by that, but
all right, but you see, the trouble is you're saying Yang-Mills.
yeah, you
I'm talking about pure
so
nonabelian gauge theory, no fermions, just the gauge fields. Just as here we had the Maxwell action, we didn't put in any coupling to fermions. If you can probably, you might get away with coupling to massless fermions.
this is not sort of
On the other hand, there aren't any massless charged fermions in nature, and there's probably a contradiction that forbids that. All right, let's see what the change in, let's just do a scalar field.
So somebody here says conformal invariance of pure Yang-Mills theory happens when D equals 4.
Not
Oh, great, really, let's see.
There's no proof, it's just an answer to a question on.
Right.
Yeah, I saw that was in the same thread.
Okay,
that
all right, so it's exactly, so all right, so it's what I said earlier. If you add terms without adding a dimensional parameter, it works. And so if we carried this out, and if I were smarter, I would be able to derive this. But at least I guessed at the right answer.
was
Okay, so pure Yang-Mills is So pure Yang-Mills is conformally invariant, right? It's conformally, not just scale invariant, right?
Conformally.
Conformally, okay.
Make it an extra credit.
All right, what?
So make it an extra credit problem.
An extra
Sure.
credit
Finish the
publication.
calculation.
All right, yeah, all right. So this is an extra credit problem, but
I'm seeing that it's called
but
invariance
you
or
get a lot of extra credit for doing. Of course, you can just look it up.
the while invariance, that's what they're calling it. They're, I guess people are associating conformal invariance to while whatever this is. But it's while, right? While.
All right, I think that the thing is this simple. This is the change in phi.
Sure.
Now, when I say that, all right, let's see what happens if we do this. So what is the change in phi comma L, phi comma L? Okay, so this is going to be twice phi comma L, the change in phi comma L. And so this is 2 phi comma L. The change in phi comma L, well, this is going to be presumably just the Lth derivative of the change in phi. And so that's going to be 2 phi comma L, the Lth derivative of yj phi comma j. And so this is 2 phi comma L, yj comma L, phi comma j, plus 2 phi comma L, yj phi comma JL, so 2 derivatives. So the change in the action is 2 phi comma L times this thing. Oh, I've already got that in there, don't I? Yeah, all right, so this is the change in the action. Okay, can we write this as a total derivative in some case? All right, so what we've got is the change in the change in the change. So you guys should watch what I'm writing and correct any mistakes, okay? Because we don't want to waste time here with mistakes. So let's lower this j. So this is 2yj comma L, phi comma j, that's this term, plus, it's a yj phi comma j comma L. Well, it doesn't really matter that much, does it? Well, right here, you see, this thing is symmetric in L and J. So this thing is actually, this term here, we can pull out. Oh, do we have two? Do I have too many twos?
I think you dropped a 2, or if you didn't.
No, I think I added it.
You got rid of it. Oh, you pulled it out to the front, I see.
Yeah. Okay. So this is equal. So one of these terms is 2 phi comma L phi comma j, and if we get rid of the 2, we can write this as yj comma L plus yl comma j. So that's one term. And then the other term is 2 phi comma L phi comma J comma L y j. And now, if this is a killing vector, we can rewrite that as
So where did the y, l, comma, j come from?
what?
Where did the y, l, comma, j come
Oh,
from? Sorry. I
you
didn't
see,
that.
phi comma L, phi comma J, that's symmetric in LJ.
Okay.
So we can borrow one of these guys and switch it.
Oh, okay. Sure.
And so we have phi comma L, phi comma J, and then this thing is 2 over D, eta JL times, I'll just write it as the divergence of Y. So that's one term. And then the other term is plus 2yj phi comma L, phi comma L comma J. And let me raise this J and lower this J. Now, can we write this as a divergence somehow? Well, one thing that's problematic here is, where did,
Could you take the? Yeah, Kevin. I think. Well, maybe not. Well, maybe. Yeah, no. So my prediction is that possibly can we take the j derivative on your last term there?
here,
Yeah, and you have 2 times phi comma L phi comma Lj, right? But let's take the 2 and make this just a derivative of phi comma L phi comma L. Could we do that? Is this okay?
oh,
Eh,
right, no, you're absolutely right. We can take this and pull out a partial J there.
Yes.
That's that.
And then take.
And, oh yes, and then that's that. So there's no minus sign. Why is there no minus sign? Or is there a minus sign that I left out?
Is there something with the phi's having a symmetry property that would produce a minus sign? I thought that.
Is this supposed to work in any dimension or just dimension 2? I see why it would work in dimension 2.
See, the other thing that's a little bit confusing me here is that we've got phi comma L, phi comma J.
Yeah, take the eta.
Oh, but we have this
Yeah.
eta. So this just brings this down to a comma L.
Yeah.
And so, oh, this is a total derivative without a minus sign.
But the d
I
has to
think.
be. Does d
Oh, it is if D is 2.
if d is 2? Yeah.
Right. That's great. So if D is 2, then this is equal. Oh, wait a minute. Is it 2 or is it? Did we have no? Did we have no? There were no. Is there 2 loose anywhere?
You mean the root is
There's a 2 over D here. There was a 2 here, but we used it when we made the
Yeah.
Austin shift. Yeah. Okay, so if D is 2, then this is simply phi comma L, phi comma L, del dot Y plus Y dot del effectively on phi comma L, phi comma L. And so this is D, dj of yj of phi comma L, phi comma L. And so it's a total divergence, but only in 2 dimensions.
Is it supposed to work in any dimension?
Well, I was just, well, 2 dimensions gets you all kinds of advantages, which is why the string theorists have huddled down there.
Yeah.
I would have thought, all right, why don't you're on the internet, what scalar field theories are conformally invariant? And, or is massless scalar field theory conformally invariant only in 2 dimensions? It kind of surprises me.
So, I have a prediction as to why it only works in 2 dimensions.
What?
I have a prediction as to why it only works in 2 dimensions.
Yeah.
So in higher dimensions, so you can so 1 plus 1 dimensional massless scalar field theory is essentially waves on a string, right? In higher dimensions, the solutions are waves on a plane, and you can have things that are not rotationally symmetric there, like solutions to the wave equation that have degeneracy. So they're not rotationally symmetric. I don't know. That's my
You
guess.
produce that in 2 dimensions too, though.
No, 2 dimensions is in 1 time, 1 space. So there's no such thing as like rotations there.
Yeah, I
So
guess it doesn't really, like, it
Yeah,
does,
yeah.
well, I mean, any unitary operator is a rotation, but it.
But this theory is so
it
much
does
simpler,
nothing to
you'd
it. It
expect
has
it to
to
be
scalar
more,
invariant, yeah.
I would have expected this to be invariant in many dimensions and
Yeah,
Yang-Mills
yeah.
only in 1. But,
Yeah, no,
well, this may be why scalar fields are so rare in the standard model, and gauge fields are totally common because the gauge fields are conformal, at least the massless gauge fields are conformally invariant, but the scalar fields are conformally invariant only in 2 dimensions. Now, I'm saying this, but I don't really understand it. Well, this was fun. So you guys did well. Bobby, do you have anything?
No, nothing that's.
Okay, so
It's
why don't we?
talk about Klein-Gordon fields.
Why don't I urge? Well, yeah, it's Klein-Gordon, but with massless Klein-Gordon. All right, do this. Is massless Klein-Gordon theory conformally invariant? And then maybe there'll be a paper saying yes, but only in 2 dimensions. Here, you get a shit.
all right.
Okay, anybody else hungry? Anybody hungry?
I'm fine, thank you.
You hungry?
I'm fine, thank you.
No?
No, thank you.
Okay. Anybody hungry? All right, I think we can turn off the computer.